Hi, hello everyone, and I hope you're all hearing me well. So this is Latifah Almulla. I'm organizing this BioElevate seminar, and as this is the first seminar, I would say welcome to all of you to BioElevate, and thank you very much for joining us today. So as you may know, this series is all about highlighting some exciting work from early career researchers in bioelectronics, and we will try to make a global scientific exchange as it's going to be online fully as well as free, and we are trying to cover people from all around the world. And just a quick reminder that these seminars are going to run every 3 weeks on Tuesday at 2 p.m. UK time. And now I'm going to share with you my screen, just in case if you haven't registered to our mailing list, please scan the QR code here to register within that and to be updated with the upcoming talks that we are going to have it soon. And just one quick announcement that at the end of the seminar of today, we are going to announce the speaker of the next seminar at the end of the today talks. So please stick with that. And we are going to announce it very soon at the end of the seminar. So now I'm highly excited to kick off the BioElevate seminar with Dr. Amparo Guemes. Dr. Amparo Guemes, she is from University of Cambridge. She is a Royal Academy of Engineering and Rotrest Research Fellow at Bioelectronics Lab, led by Professor George Miliaris. As a researcher, Amparo distinguished herself in the field of metabolic treatments based on neuromodulation. The interdisciplinary nature of her work includes signal processing, modeling, bioelectronics, and electrophysiology to develop advanced algorithms and neurotechnology to be integrated into a closed-loop platform, aiming to improve metabolic control. Amparo received her bachelor degree in biomedical engineering from Spain and her master and PhD from Imperial College London in UK. During her doctoral training, Amparo was a visiting PhD researcher fellow in computational sensory motor system at Johns Hopkins University. Amparo is an author of more than 20 publications and presentations in highly recognized journals and international conferences. She has won multiple awards from leading institutions, including Imperial College and Johns Hopkins University. She was a recipient of Raffle Dill Pino Fellowship to pursue her master and PhD at Imperial College London. In 2021, Amparo was awarded the prestigious 1851 Research Fellowship by the Royal Commission for the exhibition of 1851 to continue her research as a postdoctoral researcher for 3 years at the University of Cambridge. In 2023, Amparo work has recognized with the Engineering Award from Lawyer UNESCO UK and Ireland for Women in Science Rising Star program, which encouraged the contribution of women pursuing their research careers. She recently has been recipient of Royal Academy of Engineering and Rostress Foundation Research Fellowship to her work as a group leader at Bioelectronics Lab. Today, we are very excited that she is going to give a talk on navigating the challenge of developing a closed loop neurometabolic platform. And before we move to Amparo, just a quick reminder that we are going to take all of your questions after the talk. So please feel free to write them now in the Q&A box or raise your hand after the talk at the end of the seminars. We are going to take them all. So now I'm going to move to Amparo. So please, Amparo, the floor is yours.
Well, thank you very much for the super detailed introduction. You really went through my series, so that's very much appreciated. Thank you so much, Latifah, for organizing this series of events. This is a fantastic opportunity. I think the field is going to benefit massively, and it's really a pleasure for me to start this series. And hopefully, what I present today is it's interesting enough for this audience. So let me share my screen and start what we came here for, which is listening to our science. So as Latifah nicely introduced, I'm gonna focus the presentation on what I found are the challenges to developing a closed-loop neurometabolic platform. So to begin with, I'm going to start with what metabolism is, because most of us really work on the neurotech space, so we are aware of neurotechnology and the nervous system, but not so much on metabolism. So in case you are not familiar with this, basically metabolism is every set of processes at the cellular level that convert food into the energy that we need to carry out our daily activities. So this includes the breakdown of food into energy, the elimination of the waste products, the building and repair of tissues, regulation of hormones and substances and temperature in the body. And of course, it is massively influenced by factors such as the age, the gender, the genetics, and the diet and exercise. So when things work properly, there's no issues. What happens when there's a dysfunction of metabolism? Then we have some disorders. So one known disorder is type 1 diabetes. So essentially, when we eat in healthy conditions, the beta cell in the pancreas releases this hormone that's called insulin that allows our body to store and to use the carbohydrates that are contained in the food that we eat. However, in diabetes, there's an autoimmune destruction of these beta cells in the pancreas, and therefore this causes these very large and risky fluctuations of glucose. And this disease is, I call it like a pandemic, because it really affects over 5 million people worldwide. And well, any type of diabetes, type 1 particularly is over 9 million people worldwide, and it's forecast to become the 7th leading cause of death in less than 5 years. So in terms of economic figures, the impact is massive. So we can say that insulin, which is the main therapy that is used right now, both the drug itself, but everything else that it entails, like the pumps, it accounts for billions and billions every year. And not only these social and economic figures should motivate doing like more research in this field, but also current treatments are not optimal. So the current therapeutic approach is essentially a mixture of monitoring glucose, either through the let me get the laser point, through the what's called the continuous glucose monitoring sensors, which are these devices that provide glucose measurements every 1 to 5 minutes, combined with finger pricks. So these are required to either calibrate or to get accurate values of what the glucose concentration is. And then manually injecting the insulin using these insulin pens. Most recently, we have the artificial pancreas. So the artificial pancreas is the kind of latest treatment that is available for many people now, thankfully. And this was designed as an attempt to automatize the therapeutic approach and to make it as close as possible to what the pancreas will do. So that's why it's called artificial pancreas. So essentially, it will have these continuous glucose monitoring sensors that will send the glucose values to a controller, generally like stored like in a phone, and then the control algorithm will automatically compute the insulin to be injected using an insulin pump. So one system that is widely used now is the Medtronic 660 670G, and we can see on this top graph what the glucose control will look for a healthy volunteer. So we have, this is glucose level on the y-axis versus time, and this is a random 24-hour period. And we can see that every time that there's a meal intake, there are like some excursions in glucose, but generally we keep these excursions within the healthy grain limit. Someone in a patient with type 1 diabetes that had this closed loop system, we can see that yes, like control is kind of most of the time within this grain healthy range, but still there are some times that that glucose basically just go above and sometimes also below, and that is risky. So that means that there's still something that we are missing. And the answer, in my opinion, is that glucose is a very, very complex, glucose regulation is a very complex process. And right now we are just focusing on metabolic systems. So we are focusing on hormones like insulin and glucagon. Of course, the impact of glucose itself, but we are disregarding the important contribution of the nervous system through the action of these neurotransmitters like norepinephrine or acetylcholine. And in particular, so in overall, the not only for glucose control, but overall like metabolic control, the body basically relies on these primary neuroendocrine hormones, as we said, like insulin, glucagon, ghrelin, leptin, that basically allows to control appetite, satiety, and like how basically glucose and other metabolite fluctuations go over time. But we also have this direct neurometabolic circuitry through both the sympathetic and the parasympathetic nervous system that links all these visceral organs that are related to metabolic functions, like the liver, the stomach, the pancreas, the muscles as well, the spleen, the fat, adipose tissue. All this is connected to the brain through this neural circuitry. And this opens up doors and alternative approaches to target these metabolic functions and processes. And in particular, I'm really interested in this nerve called the vagus nerve, which is the main parasympathetic nerve. And it's a nerve that connects the brain with basically all these visceral organs in a bidirectional way. So basically signals are sent both from the brain to the organs, and that's called efferent innervation, but also afferently from the organs to the brain. But we have a gap here. There's a limited understanding on how this vagus nerve transmit metabolic information, but also we have a technical gap because we lack the technology that we need to interface with it. So recently we saw the appearance of this field called bioelectronic medicine, and bioelectronic medicine is being applied to many contexts or many diseases. Essentially, it's targeting the nervous system, in my opinion, the peripheral nervous system, to be able to target peripheral diseases. So with that in mind, basically this was just to say that there are like two types of devices that we can use to interface with the vagus nerve. So we have the invasive vagus nerve interfaces, like the one by LivaNova, who is the main company doing vagus nerve stimulators for epilepsy. And then we also have non-invasive approaches, both through directly on the neck through the skin, like electrocore, but we also have the transauricular vagus nerve stimulation, which both of them are non-invasive approaches. So the idea of my research is trying to build this type of closed-loop neurometabolic systems, where basically we have the core artificial pancreas, as we have right now, but adding this neural information both at the recording part, so basically trying to decode metabolic signals from the vagus nerve to be inputted together with the glucose levels into the control algorithms, but also the stimulation, electrical stimulation of the neural system as well, to get better efficiency of the action of these drugs or yes, that we are using anyway, like insulin. So I get like this question many times, like, is this this neural part as substitution to the pure kind of drug-based approach that we have right now. And my feeling is that no, this is something that can get that extra improvement that's needed in some cases. So of course, like this is a vision, and this is the vision that I've been pursuing for the last 10 years. But in reality, this is a puzzle of challenges. So we have many different challenges to be able to get this type of closed loop system to happen, starting from the material side to the integration, the algorithm, the interfaces. So many different pieces of this puzzle. So what I want you to do in this talk is basically going kind of one by one on the main challenges that I have identified and what solutions can be explored and what solutions I have personally explored to overcome this. So to begin with, the first challenge is on monitoring these biomarkers. So we need real time and we need continuous monitoring of biomarkers. One of them is glucose. And of course, we see that there's progress in the field. We have all these continuous glucose monitoring sensors that they become more and more reliable with time. They last for longer, but still there is some limitation because they provide very specific or very just one side of the story. So if we're recording glucose, we only know how glucose is fluctuating, know how other important metabolites are fluctuating. And therefore, we need to combine this with other metabolites. So for example, we have ketonic bodies that, and we have these kind of one-off finger prick devices that allow us to get additional information in addition to glucose. But the problem with anything that doesn't basically go to the bloodstream directly is that the sensors, and this is particularly important for continuous glucose monitoring sensors, because we are not recording from the bloodstream, we are recording from this interstitial fluid. So that means that there's to begin with, there's a delay. So the glucose needs to basically propagate from the bloodstream to the interstitial fluid, basically right beneath the skin that we collect from. And that takes some time, and that comes with delays. And these delays can be from 5 minutes to 10 minutes. And that is an issue. And the second issue is that, of course, the concentration that we get in the blood and the concentration that we get in interstitial fluid is not going to be the same. And therefore, we are not going to be very accurate. So these systems are very good to find trends. So when glucose is decreasing rapidly or increasing rapidly, these sensors do tell, but they do not provide an accurate blood glucose concentration value. So these challenge the integration into real-time closed-loop systems that try to not just respond to those changes after 5 minutes, but try to respond right immediately when changes are happening. So we really need new sensors and new algorithms to be able to improve this accuracy and the speed, mostly the speed of the glucose continuous readings. The second challenge, and this is probably more related to your work, it's on the neural interfaces. So we need to overcome this mechanical mismatch because we generally work with devices that are either like metals. In this case, these are like gold microwires. We have the commercialized silicone-based cuffs, and these are very rigid. They look like this for They are bulky, they are rigid, they are really not comfortable to be worn for a long time. So our nerves really deserve something that it looks more like that, something that really conforms very well, that it's flexible, that adapts with the tissue. And in fact, when we go to, this is a very nice graph where basically we have the Young modulus of different materials. And we see that the nervous system is in the order of thousands of kilopascals, whereas what we normally use is like hundreds of gigapascals. And we have this range of materials that will try to come as close as possible to the mechanical properties of the neural tissue. And this is an aim that we need. It's a challenge, but it's an opportunity as well. And that's why in the lab we fabricate these conformal polymeric bioelectronic devices that are based on sandwich structure of parylene C as the substrate and the insulator. Then we have gold tracks, and then where the electrodes are exposed, we coat them with this conductive polymer that's called P.PSS, that basically dramatically decrease the impedance and increase the signal-to-noise ratio and charge injection capacity. And it is really biocompatible as well. So these type of bioelectronic devices are kind of the road to achieve or to reduce the impact on the tissue and the foreign body response, which is essentially all this cascade of inflammatory processes and the healing processes that eventually encapsulate the implant, and most of the time leads to malfunction of the implant because of that. So just as an illustration of the opportunities of this type of devices, I've tried to implant them around the vagus nerve as cuffs. We can see here around the vagus nerve of a rat and a pig. You can see that it really conforms very nicely. It's really a very thin plastic that we put around. And another very important and interesting application that we recently did, my colleague Alex Boyce and me, which was trying to access the internal nervous system. So basically the internal nervous system, it's called kind of like the secondary brain, because it's this network of neurons that are placed in the wall of the gut. And it's very difficult to access because this, of course, is extremely thin and extremely fragile. So the moment that we put something rigid, we have the risk of puncturing through the lumen. And that means that the outside and the inside of the lumen are connected, and that's not a good thing for us. So we, Alex very nicely designed this device that basically has like tetrodes to be able to place at different spaced at a different specific distance to kind of try to target like this clustered structure of neurons in the internal nervous system. And we implanted successfully in the colon of rats in a chronic setup. Without having any issues, without puncturing through. So this is really good promise that this type of materials and this type of fabrication techniques have future for chronic long-term implantation. Now, the next challenge is on the decoding, because of course we need to be able to not only access the neural signals, but also to interpret them, to understand the source of them. So the problem that one of the challenges that we are trying to address here is that most of them, so there are some nerves that, yes, indeed, they just connect to one specific, let's say, process. So, for example, motor sensory nerves, they connect to specific parts of the skin or specific muscles, and therefore the kind of source where the signals are coming from or where the signals are going, it's more constrained. However, when we look to nerves like the vagus nerve, because as I mentioned in the beginning, we target basically all visceral organs. We do have multiple sources that are contributing to whatever signal we can record from. So we have breathing signals, we have heart-related signals. We also have artifacts both from skeletal muscle, smooth muscle. We do have like all these signals coming from visceral organs. So then what we need to do is to be able to separate the sources. So one solution is to be able to acquire specificity in the fibers that we are recording from. One way to do that is using these multi-electrode arrays that basically place electrodes all around the circumference of the nerve and allow us to basically capture with high spatial resolution signals that are present in some fibers and not in others. So this is an example in pigs. So pigs have a fascicular organization similar to human, and therefore this was a good case study to see, well, we have signals that are present in some channels and not others. But we can also look at the directionality of the signals to basically determine whether signals are afferent or efferent. Again, signals coming from the visceral organs to the brain or vice versa. So how can we do that? So this example is with self-folded calf electrode that a colleague from Technical University of Munich built, Lucas Heidelmegen. And with this, what we can very nicely see is that signals when the calf is implanted around the nerve, signals do propagate. So we see like this very nice propagation where basically electrodes that are close by each other have more correlation, whereas as the signal propagates, then there starts to be a gap, basically. However, when the calf is not around the nerve, there's really no propagation, and therefore we don't see that profile. So these two approaches are very interesting because they provide basically the whole picture of how the nerve is conveying information and allow us to be able to detect where this information and how it's being transmitted. The propagation does not only allow us to determine the directionality, but also which fibers are being activated. Because if we know the velocity of those fibers, which is something that is widely known, and we know this how like the separation between the electrodes and the time that it takes from one spike to reach the end, then we can compute the velocity and determine the fibers. And we are in the process of testing all this in chronic animals as well. And this is an example of how these implants look in rats. Another solution to be able to tackle the decoding problem, it's basically to be able to access specific neurons using spike sorting analysis from each of the electrodes. So our electrodes are really small. They are like around 50 microns wide. That means that we can really access with high spatial resolution, depending on where, even like single neurons. So for example, this is one of the tetros that I just showed before. When implanted in the colonic wall. And we could see that we were recording kind of single unit activity. And in fact, we could decode 3 neurons. So this was done by Dion's lab and very nicely we can see that these neurons have like the properties that we will expect from neurons. So basically a refractory gap, but also we can see how neurons relate or are connected to each other. So this type of decoding or kind of single unit processing strategies are very useful to be able to go even farther on analyzing what we are recording from. But also, we can use like a strategy similar to what is done in EEG, where basically we decompose the signals into specific frequency bands, and each of these frequency bands relates to specific type of cell that we're interested in kind of isolating. So for example, we know that in the context of the gut, we have the interstitial cells of Cajal that are very low, very low frequency, below 0.2 hertz oscillations. We have smooth muscle that has two type of activities, slow wave or faster waves. Then we have skeletal muscle, EMG. This is mostly artifacts from the abdominal area. And then we have the neural activity, which is this very high frequency over 300 hertz. So when we get our signal, which is a mixture of all this, and then we decompose them into frequency bands, each of these rows is a frequency band, then we can clearly isolate the response from one source to another. And in fact, this is the case where we were trying to evaluate the response or the activation of the entire nervous system in response to stress. And we can see that on the first day, the activation in basically all the tissue types was high. And as the animal got exposed to the exact same environment over time, the response will decrease. And this, it's extremely interesting because we are seeing this acclimatation process, but very interestingly, the skeletal, the EMG band does not show that profile of kind of reduction in the activity, which, as I mentioned, this links more to artifacts or basically with the rat just moving around. So independently of whether the rat is moving or not, we can clearly isolate the response from all these different tissues. So this really opens up new opportunities because it's a combination of two challenges and different type of solutions that allow us to open up the like this type of accessing this type of events that we couldn't see before. So once we have collected the data, we need to integrate everything, like from chemical sensing to neural sensing and metrics into the control algorithm. But this is a challenge by itself because we are integrating here two different modalities with extremely different timescales. So the chemical sensing, glucose basically fluctuates in the order of minutes, and then longer term changes can happen in the order of hours, weeks, even months. So these metabolic changes are very slow. However, we are also interfacing with the nervous system, and the nervous system, as you all know, it talks with action potentials, and these action potentials are extremely fast. So we are talking about millisecond scale. So we are trying to merge together a system that communicates or transmits information in the millisecond scale with something that changes in the minute, over the minute scale. So these very different timescales for metabolic and neural dynamics basically highlight the need for a highly adaptive and flexible closed-loop system that can respond to this type of signals in real time across multiple timescales. So this is challenging, of course. So yeah, we in the future efforts will need to go in this line. And just the last challenge, if it was not enough, is basically if we want to interact and to stimulate, we really need to know what we are doing. We don't know yet the mechanisms behind neuromodulation responses. So sometimes, like, there are more and more papers that are published that they do see changes after stimulation, but the reality is we don't know the underlying physiological processes. And this is something that is kind of at the core. And probably what we see, it's a mixture of responses, because you can see, like, the scenario is very complicated. There's a lot of directly and indirectly and interactive relationship between all the organs, and therefore the fact that we stimulate one part doesn't mean that it's constrained to that. We may have cascade of effects. So we really need to spend time into understanding what are these mechanisms behind, to be able to develop precise and effective neuromodulation strategies over the long term. So the goal, hopefully, is to put all these pieces together into developing these closed loop systems or devices. Of course, the road is long, but this offers a lot of opportunities to work in. So, like, from basically all different fields, everything within this same umbrella of closed loop neurotechnology devices. So just the last 5 minutes, I think I'm on time. I want to tap on some advice or some like tips that I put together uh, based on my experience on when pursuing a career in academia. Of course, I'm an early career researcher as well. So if you talk with someone that is more experienced, they may say differently. But so far, what worked for me is the following. So to begin with, I want to highlight some key skills that I found that is extremely useful. One is having very good communication skills. So this is something that you may not feel comfortable right now, but it's something that definitely can be trained. So anytime that you have to practice presenting posters, presentations in the lab, any opportunity is a good chance to improve your communication skills. Because again, this is something that really you get better as you do. Another skill that I think is very important is the resilience in the face of challenges. So I think I've already covered enough the challenges, so there's no need to go through that. But of course, this is something that it's skill to have if you want to pursue a career in academia. There's gonna be a lot of blocks, but we can't basically get small in the face of those challenges. We need to get bigger and see those as opportunity to keep moving the field forward. Then another important skill for me, it's being really responsible with your research. So there's an urge to have positive results, or like the feel, or there's a pressure to do that. The researcher should be on top of all of that and above all of that, and prior to anything should be ethics and being rigorous in the way that we conduct research. Another very important skill is critical thinking. So we need to be able to challenge anything that we are reading or that we are hearing or that we are doing. So this critical thinking for me is one of the most important keys, skills to be able to continue in research. And then, of course, management. And management is not only about time management, it's about learning how to do the best or make the best use of your resources, funding, personnel, facilities. So it's really optimizing what you have, the resources that you have to reach your goals, essentially. So how to build strong academic profile? So the first for me will be to, of course, be curious, be ambitious in your ideas, be basically passion driven. But of course, you always need to be to keep perspective and to stay aware of the big picture trends, how the field is moving, and basically develop your own interests, but being mindful of what's going on. Publish strategically. So there's kind of this trend to publish, or the what's called the publish or perish culture. But it is our chance as early careers to change it. We should prioritize quality over quantity. And what I would suggest is really learn how to write good papers. That's an important, like another important skill to have. Aim for impactful journals or conferences in your field, and also collaborate with other authors across labs, across institutions, because that's gonna open up your vision of the field. Then make yourself visible. So this is very important. Try to present your work as much as you can in conferences, online, engage in academia and in X or other platforms, ResearchGate, build your Google Scholar, your ORCED profiles. Try to make yourself visible. The problem with academia, I found, is that there are too many things that we can do, and most of the time there are too many things that interest us. So I will say that try to say yes, but strategically. So for example, you will be offered to do some teaching or to do some outreach. These are absolutely, I always encourage everyone to have these as part of your profile. But be mindful of your time. Again, manage your resources, and one of your most precious resources is your time. So say yes, but learn also to say no when you have to. And then finally, this is my final slide. From my experience, some practical tips that helped me is try to find good mentors. So it's the people that you surround with, they make a difference. They can make the process easier if you learn how to do things, and if you are like accompanied basically throughout the process. Learn the funding game as early as possible. Try to apply for small grants, for travel awards, whatever opportunity for starting to write for fellowships or grant is a good chance, because the rejection is going to be very high. That's something that we know. But again, we get better as we do. So the more you write, the better you'll get at it, and the more chances to get to secure money. So practice it. Try to build your own network. So go again. This links to being visible. Go to events where you can connect to people. This is building your own community. Connecting with external collaborators, not just people from your lab or your immediate community. Try to attend summer schools, for example, workshops, academic retreats, any events, outreach, whatever. All these are very important, at least from my experience. Stay resilient again. Embrace rejection, because this is a marathon. Rejections are normal, so we just need to keep showing up. That's the aim. And then research is definitely not linear. So what matters at the end of the day is not how many times you've tried things, is how much you've progressed. And every single failure point is a step forward. It's more learning, it's more knowledge. And sometimes we are so focused on the day that we forget about that. So it's important that from time to time you look back and really think about all the progress that you've done. So we are all in the same kind of path, and it's important to be mindful of that. So these are things that have worked for me, but the most important one is this one. Define your own version of success. So academia has many paths. There's more like research path, more teaching part, more translational, just being national, more international. Do whatever matters for you and aim for that. There's no single solution. There's not a one-fits-all solution. Build your own version of success. And with that, I just want to finish by acknowledging my group, the Bioelectronics Lab at the University of Cambridge. Of course, my collaborators, both in Cambridge and abroad, and the funding support from the Royal Academy of Engineering and Roasters, most recently the worshipful Company of Scientific Instrument Makers, and previously the Royal Commission and the for Women in Science, the L'Oreal Foundation. So with that, thank you very much. I'm really looking forward to getting your research or more career questions. And feel free to reach out to me to this email address, and I'll be happy to continue the connection. Thank you so much. Hopefully I've been on time, and I am very sorry about the technical issues before.
Thank you so much, Amparo. That was really interesting and insightful talk, scientifically and both about how to improve yourself academically in terms of skills and others. So just a quick reminder, if anyone has a question, please, it's the time now to raise your hand or write them in the Q&A box. And we are going to take the questions one by one. So I think there's one question now on the box, so maybe we can jump to that. I will read it. It says, it's from Jen. It says, can you please share perspective how to verify the stimulation of vagus nerve is effective for diabetes treatment? The recipe of electrical stimulation is complex, and vagus nerve connected through lots of organs, not only insulin related stuff. So he has 3 questions. Let's take them maybe one by one if we have time.
Yeah, that is one of the main questions. So my research is right now not focusing that much on the stimulation part, but I've done some. So essentially what you want to get is specificity. And you can do that through different strategies. One of them is changing the location of stimulation. So if you target closer to the brain, of course, you're going to be targeting many more organs. So cervically, you will target the heart, the lungs, and all that's going to affect. So one strategy is to move closer to the organ of interest. So you really want to target the pancreas, develop interfaces that can be placed closer to the pancreas. An alternative approach is trying to acquire this selectivity by doing these multi-electrode arrays with to stimulate specific fibers that are pre-identified that target specific organs with very high spatial resolution. So there are teams out there that they are working very hardly and very successfully on clearly defining which fibers or what's the functional organization of fibers within the vagus nerve at different locations along the nerve. And there are also groups that are trying to get this specificity or selectivity in the stimulation on those fronts. So depending on that, then different therapies could be developed.
Cool. So the second question is, what is the spike sorting method for the result on slide 19, if you remember slide 19? Template matching or traditional triangulation? The autocorrelation correlogram is a bit different from usual one with two ends going up, not going down.
So the spike sorting technique, so this paper is under review right now. We have a preprint, but that precise results are not included in the preprint because those were added later on. So hopefully you'll get the full methods clearly explained in the near future, published. But basically, this is the same type of analysis that is done in the brain. So there's an open source software that is used for spike sorting. So I can send you the details if you're interested in specifically. But it's, if I'm not mistaken, so it's thresholding, spike thresholding, and then clustering. And then based on that is the correlograms, essentially.
Great. So I think for the interest of time, maybe we can take the last question for now, if no one has any other question. So the last question would be, what is the main motivation to use pyrrolin C as electrode substrate if mechanical mismatching is a concern? What would be the next electrode type?
So pyrrolin C, it's true that the Young loss maybe higher with the same kind of or using same dimensions, but what we are going is very, very thin. So our electrodes are 4 microns. So the mechanical mismatch is further reduced that way. But it is true, it's still not the most optimal material to be used as a substrate. So for example, using pure PDMS devices is an alternative approach that could be explored. It's actually being explored. There are papers out there. So basically using these materials that really mimic as much as possible the electromechanical properties is the way to go.
Great. Thank you so much again, Amparo, for this nice talk and really nice answering all of the questions that they have. And I think now we can start sharing and announcing who's going to be the next speaker of the seminar. So our next speaker for the next seminar is going to be, if you can see my screen, yeah, is going to be Scott Keane from Rice University. Please feel free to scan the QR code here and to read the abstract and to register to the next seminar. And with that, I would thank all of you for being here today. And until then, we will see you soon in 3 weeks. Thank you so much and take care.
Thank you.
Thank you.
Bye.
Bye.